thing that we wanted to know is about superheated vapor. So if you can recall back from the image here, okay, so this is a PV diagram, okay, and then you have gas, for example, like going up, for example, this at this particular point, this is where actually it represents the superheated vapor region. Similarly, if let's say you are having the graph for TV, okay, TV diagram, so whatever that is beyond this curve, which is somewhere around region here, this is where actually we have what we call as superheated vapor. So superheated vapor, it is the region to the right of the saturated vapor line, and at temperatures above the critical point temperature, as substance exists as superheated vapor. Okay, so whatever that it beyond the saturated vapor line, this is what we call as superheated vapor. In this region, temperature and pressure are independent properties, so it's no longer dependent. It is an independent properties. So if you want to compare, for example, saturated vapor, superheated vapor is characterized by lower pressure. So usually the pressure, if let's say the pressure compared to saturation pressure is much lower compared to given temperature. So this is where actually if you compare this is T and V, okay, T and V diagram. But if let's say you have a P and V diagram, okay, so you will notice that actually at the given temperature, the pressure will be lower than saturation pressure, and it will have a higher temperature compared to at the given pressure compared to the saturation temperature, okay, and it will actually have higher specific volumes. For example, like the V is much bigger than VG, okay, it's beyond VG. It will have higher internal energies. The internal energies will be higher than internal energy at the saturated vapor at any given P or T, and it will have higher enthalpies, which is beyond the Hg at given P or T. Okay, so at the specified pressure, superheated vapor exists at the higher H, which is higher enthalpy than the saturated vapor. So this is from the diagram here. You can see that the enthalpy here is bigger than the vapor enthalpy at the saturated vapor. So let's talk a bit on the compressed liquid. So what is a compressed liquid? If you are referring to the diagram here, whatever that is in red line is already reached saturation, but the red line which is before the curve is what we call as compressed liquid. So compressed liquid properties depend on the temperature much more strongly than they do on pressure. So at this particular region, it depends highly on the temperature. Okay, it depends highly on the temperature rather than on pressure. So a more accurate relation, if you want to determine the enthalpy at this particular stage, for example, the enthalpy of the fluid at certain temperature plus with the saturated vapor point at that particular given temperature, and then you have a pressure minus with the saturation pressure at that particular temperature. Okay, so if let's say you were given pressure and temperature, your volume, your internal energy, your enthalpy, it is almost approximately the same as the saturated vapor properties at the given temperature. And the compressed liquid is characterized by higher pressure. So usually the pressure is much higher than the saturation pressure at the given temperature, and usually it is much lower temperatures compared to saturation temperature. It has a lower specific volume, okay, it has a lower internal energies and as well as lower enthalpies. So this is the characteristic of the compressed liquid. And another case that we wanted to look at is actually the saturated ice water vapor table. So if you are looking at table table A8, in this particular table, the terms SUBL, sublimation, refers to the difference between the saturated vapor value and the saturated solid value. So what is actually happening here, when the temperature of a substance is below the triple point temperature, the saturated liquid, solid and vapor phases exist in equilibrium. Okay, if you notice that if you have a below triple point, okay, if you look at back the phase diagram, if I could draw a little bit here, if you have a phase diagram which is actually I would say T versus, sorry, maybe it's P versus T instead of PV or TV, you will have a diagram which will look like this, somewhere like this. Okay, and then at this particular point you will have what we call as critical point, and this is the point where actually this is what we call as triple point. Triple point is where the solid, liquid and gas coexist together. Okay, but beyond that, okay, again, if let's say you have this, right, this is the critical point, but below that is actually is a region where the saturated solid and vapor could exist in equilibrium. So again, we define the quality as the ratio of the vapor mass to the total mass of solid and vapor in the saturated solid vapor mixture. We can also use quality, okay, but here the quality is actually the mass of the solid, mass of the vapor, okay, the mass of the vapor divided by the total mass of the solid plus mass of the vapor. So here you can determine the quality. Okay, so the process of changing directly from the solid phase to the vapor phase is called what we call as sublimation. What happened here is that the vapor it itself doesn't become liquid first. It straight away or we call that from solid, it doesn't become liquid first, kan? Kalau ice tu, it doesn't melt first to become liquid, only then after that it become vapor. But what happened here is that the solid, which is the ice, is transformed straight away to become vapor. So this is the process what we call as sublimation. Okay. So if you want to get the data for saturated ice and water vapor, it is given in table A8, and the specific volume, internal energy, entropy and so on, it is also calculated similarly to that of saturated liquid vapor mixtures. And then this is where we have X and we have also Y. Y ni, it can be the enthalpy, it can be the internal energy, as well as it can be volume, right? Okay.